So multi-arm bandit. What is my multi-arm bandit? First, we're going to look at what is a k-arm bandit problem, and then what is exploration, and its difference from exploitation. Reward and regret function, bandit algorithms, and then in the end, I'm going to show you the performance comparison of those algorithms. Suppose there are single state S. So you are in this state. Okay. Now you have k actions. Those are the k actions. You can sample reward of actions using calls to simulators. Sampling action A is like pulling a slot machine arm with random payoff function. This makes sense, right? If you are arriving at a casino, you have three, this is K slot machine over there, and each one, but if you pull it, it's not going to be deterministic, the return. You pull it, and then you got a random variable out. You pull it again, you got a random variable out. You were saying, I may be getting lucky. Always the big return, right? But no, this one has a distribution of return. This one has another distribution of return. And you are just the sample. You are the one random realization, one random number generated from the distribution. But what do we want to do? We want to do experiments, because I can do experiments. I can try this one a few times, this one a few times. Then I found, oh, this one gave me big return. Okay, like almost my body. Next time you go to the casino, you choose the second one. That one has a higher return. Okay, but we need to find out which one has a higher return. So this is what we want to do. This is called a k-arm bandits problem. Is that clear? So you have a tube that is A and reward. And the A is known set of k actions, k arms. So RA is the return. If you select an arm, the return depending on your action. But return is the unknown probability distribution of a reward. So at each step T, the agent selects an action. The environment generates a reward. This reward is from this distribution. And you choose an action belongs to how many arms you have over there. The goal is to maximize cumulative reward. Okay? And the expected reward of A is actually, if you have selected action multiple times and you take the average, this is the expected reward for a particular arm. If you have done 1,000 times, then you do the expectation. If you do 1,000 times, what can you get for a particular arm? You can get a bunch of return, right? Random variable. Then based on the random variable, you can evaluate what? You can evaluate the distribution. And the distribution, obviously, you need the mean and the variance. Suppose we know the distribution. This is a distribution. This is slot machine 1, slot machine 2, slot machine 3, and to 10. Okay? Now, which one you are going to choose? This is a distribution of return. This is a reward distribution. For the first one, it has this distribution. The mean and the variance. But the variance, here variance it seems to be the same. But some of them variance can be smaller. Some of them variance can be extremely big. Okay? But for this one, if you are going to choose a slot machine, which arm are you going to choose? 3, right? Give you the overall average return. Now, this is not just for gambling. This could be used for clinical trials. So you can have possible treatments, okay, multiple arms. For example, a patient comes and he has some kind of illness or disease. Now you can have maybe 4 different kind of drugs. Now, arm pulls is the application of the treatment to this individual. Now, reward is the outcome. objective is to maximize the cumulative reward, maximize benefit to the trial population, to find the best treatment as quickly as possible. And online advertising too. So you can have display different kind of ad for a web page. Okay, this is actually, you find that every time if you click a YouTube, they're going to generate some kind of advertisement, short video, 4 seconds, how they are going to choose that video. And they can choose different video type for that page. Okay. Now, on post display an ad upon a page access, and the reward is a click-through. And the objective is to maximize the cumulative reward, maximize clicks, or find the best ad quickly. So you want to display the ad that this customer is interested in. Then you based on the video itself, and then you can how they are clicked. If you click, they got a reward, right? So they are actually doing the sampling. This is a real algorithm behind how they display the ad. Now, what's the simplest way to do it? If you have k actions, you just pull each one of them maybe 1,000 times, and then you do average. You see which one is the best. So uniform bandit algorithm, you pull each arm W times. This is called uniform pulling. You return arm with the best average. So use this one, you do it W times, W times, W times, and then you do the average, and whichever gives you the best average reward, you go with that. But can we make a more efficient bandit algorithm? Because this one needs you to do W if you have k, W times k times, right? So non-uniform sampling. So if you have already found the arm is pretty bad, we should be able to eliminate it from consideration. You don't have, for example, you have pulled 100 times. You find out it's pretty bad. You still want to try it more? You want to eliminate it from consideration early on. So idea is try to allocate more pulls to arms that appear more promising. Okay? Why? Because if you pull this one is pretty bad. Every time you insert $100, you eat it. And then you pull 100 times, you still insert $100. Are you crazy? This one always take you $100. But this one, okay, you give $100, it return maybe $200 to you. And next time it take $50, okay? And next time it return $1,000 to you. But you still want to try this one 1,000 times, or you want to try this one a little bit more. Because you want to maximize the cumulative reward that you receive. By doing more experiments, you're losing more money too, because you have to pay to test the outcome. So this is called exploration and exploitation dilemma. So online decision making involves a fundamental choice. Now, if you find one is pretty good, of course you want to exploit that. Make the best decision given current information. Because this one gave me maybe $200 return. I should try this one more. Instead of that one, take my $100. But exploration means for some of them, you haven't tried enough. You want to try more so that you can explore. Maybe that one, you are just bad luck, got to eat. Maybe next time if you insert, you got $1,000 back. So the best long-term strategy may involve short-term sacrifice. So gather enough information to make the best overall decision. Okay? And then examples. We have restaurant selection. So you can go to your favorite, you have already tried a few restaurants, right? And then you can go to your favorite restaurant. And the exploration is you try a new restaurant. So online banner advertisement, you always show the most successful advertisement. Or you just try, sometimes you randomly try a different one, see how it works. Or you're drilling. You drill at the best known location, or you drill at a new location to explore. Game playing, you play the move you believe is the best, or you play an experimental move. So the action values. action values, this is the action. You get a reward, but you are focusing on the expectation. Okay? So this is called Q. Optimum value V star is equals to QA star. You want to choose the best action that give you the maximum reward, maximum expected reward. The regret is the opportunity loss for one step. If you know the best value, then you know if you try and you got a reward, you try, you got a reward, right? Then this is called a regret. But most of the time, I don't know this best value. But if I know, this will be my regret. Now let's assume we know. The total regret is the total opportunity loss. So you try n times, and how many you have lost. Okay. So minimize cumulative reward equals to minimize the total regret. Yeah, you do have regret. You instead of $100, it was eaten by that machine. You say, oh, I so regret it. I shouldn't try this one. And you try it again. The second regret. Right? You keep regretting. You want to minimize your regret. Okay? You want to maximize the cumulative reward. So counting regret. The count NTA is the expected number of selection for A. See, this is A action you have chosen, and you choose it n times, the count. The gap is the difference between the value, between the optimal action. So if you have optimal action, you have V star, and then the QA. Then this is the gap, is actually the regret. So regret is a function of the gaps and the counts. You have this one. This is a regret sum, right? Now it's actually equals to expectation n times the V star minus QA. It's actually equals to expectation, the count, times the gap. Okay. So a good algorithm ensures small counts for large gaps. Okay, small counts for large gaps, and large count for small gaps. So problem gaps are not known. You don't know it. If you know V star, problem solved, but you don't know. If you know this machine, give me the V star. Why do I need to try? I just choose this machine. That's it. So if algorithm forever explodes, it will have linear total sub-regret. If algorithm never explodes, it will have linear total regret too. Now, what we want to do is we want to choose sublinear total regret. This is gradient, and this is Epsilon gradient, and this is decaying gradient. Now I'm going to show you what are the three. So there are different ways to maximize the cumulative reward and minimize the total regret. Those are different algorithms. This is a naive exploration. And then you can add noise to the gradient policy. This is Epsilon gradient. And all optimistic initialization, assume the best until proven otherwise. All optimization in the face of uncertainty. Okay, perfect prefer action with uncertain values. So I'm going to talk about this is a famous UCB algorithms, and also gradient bandit, preference function over action. The first one, what is a gradient algorithm? So we consider algorithms that estimate QTA. You can try a few times. Now you estimate QTA. Now, this estimation is done based on the Monte Carlo evaluation. So how do you estimate this? You get a reward every time when you select A, you get a reward, right? Then you just divide by how many times you choose this action. This is the average. Each time you choose this action, you get a reward. Next time you choose different action, you didn't add it to that one, right? For this action. And next time you choose this action again, A again. And then you make indicator function to be 1, and then times RT. Otherwise, you make it 0, right? And then divided by this, this is the average. The greedy algorithm select action with the highest value. That means you always maximize the action. Action belongs to this set. You just choose the one that maximizes the QTA. So greedy can lock on the suboptimal action forever. Greedy has linear total regret. But what is Epsilon gradient? Epsilon gradient means, okay, you can have gradient. Okay, this one is pretty good, and you should exploit. You should continue to select this action. You have already found this one is max, right? So it means that with probability 1 minus epsilon, epsilon is a small value. That means if epsilon is 0.1, then this is 90%. You're going to choose this one, this action that currently give me the best return, right? And then 10%, you're going to choose a random action. For example, you have 5 actions. You just randomly choose among these 5 actions. This is called exploitation. This is called exploration. So constant epsilon ensures the minimum regret, okay? And epsilon gradient has linear totals of regret too. Now, what is the incremental? Because you want to do it online. You pull and then you do it with time. So how to evaluate the Qn plus 1? Qn plus 1 is you go from I from 1 to n, all the returns, you add them together, you divide by n. This is the average, right? But what we should do here, you should put Rn here. And then from 1 to n minus 1, this is actually, you see here, this is actually Q. And if you pull this one inside, okay, then this will become Qn, okay? And this is Qn plus 1. This is become Qn. This is Rn. And then you pull this one over here, and you expand it a little bit. Then you have this Qn plus 1 equals to, this is iterative calculation, iterative function. Qn plus 1 equals to Qn plus what you return, what is the return for the nth trial, minus Qn, the gap. And then 1 over n. Okay? So this is incremental implementation. Oh, okay. 2 ways to do it. When you calculate average, you can just, take the overall average. You got to add the numbers. Or you can do it iterative way. You know Qn. And you don't need to calculate everything behind. You just need to know what is n, Rn, and then minus Qn, then 1 over n, plus Qn. Immediately you got a Qn plus 1. Okay, this is called online implementation. This is offline. They're same thing, but you're just doing it in different ways so that it make it faster. Because you have already calculated Qn. You don't have to do it again. Because here you're going to do all the sum together. Okay, now let's look at this algorithm. So in the very beginning, you have k actions, and you make sure all the QA, expected reward for this action, is actually 0, and the count to choose this action is also 0. This is initialization. Now we're going to repeat forever. Okay, repeat forever means now you're going to with probability 1 minus epsilon. And if you have a tie, okay, if you have a tie, for example, 2 of them give me maximum value, you just break tie randomly. And you choose the action, give you the highest return, expected return. Q is expected return. That means average. And then all you can do with a probability epsilon, you randomly choose an action. And then once once this action is chosen, you just run the bandit. You just pull the arm and see what's the return. Then this return is for this particular action for this time, right? Then you have the count should plus 1 because you tried. This is one trial, right? And then the QA should be updated because you got a return. Although beginning is 0, then you keep doing this iteratively. Then you will be able to, based on the QA, then you choose the new action again. Based on QA, you choose the new action again. You repeat forever until you got all the QA values. For all the action, each action you have a return, right? Expected return, that's Q. Now, yes?
Is it possible that some of the actions, like we never visit them, because if we have like 10 actions and we try these, they have some reward, and now you have a positive QA, and these rewards are going to be 0 for the actions that you didn't select. So
very good point. So, but here you have probability epsilon to choose a random action, okay? And if you have a probability epsilon, that means you can try most of the actions. You can try the code, and most of the action will be sampled. And later you're going to have a distribution over all your A's. Okay. So this one is the online implementation, iterative implementation. Okay? So we are using the new estimate equals to the old estimate plus step size. This is my step size, 1 over n. And then target minus the old one, target minus the old one. Gap. However, this could be non-stationary. Non-stationary case, you want to weigh the recent rewards more heavily than the long past ones. That means you are not going to use 1 over n anymore. Because 1 over n, how did you get 1 over n? When you get 1 over n, the weight, you see the weight for every R1, R2, R3, R4 to Rn, the weight is 1 over n for all of them. That means you weigh all the reward in the past equally. But you want if you want to weigh the most recent reward more heavily than the long past ones, you just don't use 1 over n. You use alpha. You can choose this alpha. Because if you choose this alpha, it will become alpha. You see, this is like a regularization. It's a balance between what you have currently and what you have old estimate. And this is a new estimate for the new trial, new return for the nth trial. And then you can do the iterative. You see here, this current one weight alpha, but this one is 1 alpha alpha. See, the weight is getting smaller. So this is why we're using Qn plus alpha. You are changing 1 over n to alpha. Now, we talk about epsilon gradient, and you should be able to, now am I making sense? Okay? Now the next one is a little bit tricky. That means previously, if we try this algorithm, we initialize QA to be 0, right? But the next one is very optimistic. That means we're going to initialize QA to high values. The same algorithm as shown in the previous one, but you just initialize QA to very big values. Okay? Then you update action values by incremental Monte Carlo evaluation. Now still the same iterative function. Okay? Count. Now you encourage for this one because you have very large Q value. Okay? And then you're going to encourage systematic exploration early on, but it can still lock into suboptimal actions. So it's better to use greedy plus optimal and epsilon greedy plus optimistic initialization. In this way, you will be able to have linear total regret. But can we do better? The do better, previously, we didn't really change epsilon. Because when you do the exploration, 1 minus epsilon and epsilon, once you fix epsilon, it doesn't change anymore. But as you try those actions more and more, all the action you have already tried 1,000 times, it doesn't necessarily you go with fixed epsilon. That means epsilon can getting smaller and smaller. In the very beginning, you encourage exploration because you haven't tried enough yet. Then you give a big epsilon. And later, when you try enough, the epsilon should be smaller. So this is called decaying epsilon. So we're considering the following schedule. That means, you see this epsilon. Originally, it's 1. Okay, this one is pretty big. But as you try t more and more, this one getting smaller, right? So when it is smaller than 1, then epsilon t will be getting smaller too. But when you are, because epsilon is like a 1 minus epsilon and epsilon, it's like a probability, so it should be less than 1. So minimum 1. When this one greater than 1 is still 1. Okay? So decaying epsilon has logarithmic asymptotic total regret. Unfortunately, schedule requires advanced knowledge of gaps. So we want to find an algorithm with sublinear regret for any multi-arm bandit problems without knowledge of R. How to do that? So this is called optimisms in the face of uncertainty. Okay? You see here, you have 3 actions, A1, A2, A3. Okay? And which one you should choose? Which one you should choose? And this is my current estimation of the distribution. Based on what I have right now, I should choose 3, right? But this one has a high uncertainty. High uncertainty, if I keep choosing this A1, this distribution might change. Okay? So that means not only I need to consider the mean, I need to consider the uncertainty too. That means the range. Previously, we only consider average, Q. But now we need to consider the uncertainty of our estimation. So which actions should we pick? The more uncertain we are about action values, the more important we should explore that action. Make sense? So it could turn out to be the best action. Make sense? So after picking the blue action, we are less certain about this value and more likely to pick another action until we home in the best action. So this is the idea. You want to estimate an upper confidence UTA for each action. Okay? So we want to, not only we are using Q, but also we are using the U. U is the uncertainty. Okay? Such that QA less than this one plus this uncertainty with higher probability. So this depends on the number of times NA has been selected. That means an action. If you select action, like if you count, okay? If it's this action, you have a very small. You didn't select enough time. Of course, the uncertainty is large. If you select action a lot of times, that means the uncertainty is small. Your estimation is more accurate. So how to define this UT then? We need a UT. Because we need to combine UT and my expected reward so that I can select the best action based on the balance between my mean and the variance. This is my mean, this is variance for an action. For an action, you have a reward function. That is distribution, right? This is the expectation of the reward. This is the uncertainty of the reward. Okay? So you want to balance between the mean and the uncertainty. So in order to do that, you know, this is a expectation. Expectation, so if you have x1, xt, IID random numbers. Now that xt, this is sample mean, okay? So the real population mean expectation is greater than the sample mean plus u. This is less than expectation minus 2tu squared. This is a Hopkins inequality. Okay? Now we are going to use this Hopkins inequality to define my UTA. So my UTA should be QA greater than this one, should be less than this one based on this equation. Make sense? So this is uncertainty, this is uncertainty, this is QTA, which is less than this probability. So we are very sure if we QA, the real value, is greater than the estimated value and uncertainty less than this probability. So if we pick the probability, then we will be able to derive UTA. UTA will be minus log p to NTA. Now let's pick the p to be t minus 4. Okay? So that's then ensures we select optimal actions as t goes to infinity. That means UTA will equals to 2 log t over NTA square root. Now let's just put this UTA into the equation. That means now we are going to UCB algorithm is now AT equals to argmax QTA. You just add QA plus this 2 log t NTA. You see here, this is NT, right? NT count. You choose a particular action, how many times? If this count is small, what's going to happen? Uncertainty is large. If this count is large, that means uncertainty is small. In this way, you are actually balancing between the average and the uncertainty. Okay? And in the algorithm, in this algorithm, you see here, what you are going to do is you just replace this QA plus with the QA plus 2 log t over NTA square root. Then this will be the UCB algorithm. Okay. Now the next one is a gradient bandit algorithm. Now you're going to maintain a preference, HTA, for each action. Okay? So HTA is a preference. You see, this is exponential, and then this is all the actions you have, and this is a proportion. This is actually a softmax function. What's the probability you're going to choose A? Equals to the preference function, exponential preference function, then divided by the summation of the preference function for all the actions. A particular action divided by all the actions. This is a pi TA. What's the probability you're going to choose this action? So the larger the preference, the more often that the action will be taken. That means you are adding a preference to the action. But the preference has no interpretation in terms of reward. The learning algorithm is based on the idea of stochastic gradient ascent. On each step after selecting the action, receiving the reward, the preference is updated as follows. You see here. This is very neat. Okay? You see, this is a preference, right? This is a new iteration, t plus 1, actually equals to the old preference, and then plus the reward minus the average reward in the past. You have, and then alpha. But you add a 1 minus pi t at, the one that you have chosen. But when you add this one, you also update the preference for all other actions. That means you update the preference for all the actions. Once you choose an action, you get the reward. You update the preference function for all the actions. Okay? This is for all the actions doesn't equals to the AT. So RT is the average of all the rewards up through and including time t. So far we talk about different algorithms. We have UCB, Epsilon Gradient Bandit, and Grady with optimistic initialization. Obviously, UCB is a pretty good performance. So the summary right now we have discussed so far. We have recovered several principles for exploration and exploitation. The first one is naive. You just do the average and pick the one with the average. And then you have optimistic initialization. Or you consider average and uncertainty at the same time. Okay? And sometimes if you didn't try that action enough, you want to exploit with higher uncertainty values. The gradient bandit algorithm is actually preference function based. Okay, so this is I give you some introduction on multi-arm bandit problems. This most of the time in your research, sometimes you may be able to use those algorithms. And in the next class, I'm going to show you the Amarkov decision process.